Okay, so today we are going to do the first section of Geology Notes. We're going to go through plate tectonics and the different types of boundaries you would see with our different types of plates. So, let's start first just with the structure of the Earth. There's going to be four main layers to the Earth, so we'll start with the inner layer is called the core. And there's an inner core and an outer core. Something that's kind of interesting about the inner core, even though it is the hottest core, it's actually solid. Really, really high temperature and pressure in there. It's mostly made out of nickel and iron. And then the second layer is the outer core. This one is liquid. It's cooler than the inner core. It is also made out of nickel and iron. And the core is thought to generate a magnetic field that we're actually going to be talking about a little bit later. Oops, let me move this. Okay, and then your next step up from your cores is going to be your mantle. This is the largest, the widest part of the widest layer of Earth. It's made mostly of oxygen, silicon, and magnesium. And the rock is called peridotite. Now, something we need to understand, this is actually going to be really important when we get into our plate tectonics here in a second. At the bottom, it is solid, but as we get closer to the top, as it says here, it's going to become more plastic because it's going to be molten. And this molten mantle is what's going to actually move these slabs of rock around up here. Okay, now for the mantle, we're still right in here. There's actually two upper layers. There's the asthenosphere and the lithosphere. So the asthenosphere is the slightly molten upper mantle, and it flows, and that's where magma actually comes from, the magma that we would eventually see coming up through volcanoes, which would become lava. And then the lithosphere is made up of the uppermost part of the mantle, and then it's actually a lower crust. So it's actually a little bit of the bottom crust, a little bit of the upper mantle, and these are our actual plates, our tectonic plates. So the asthenosphere is going to be the molten stuff right here that's right below our plates. And again, the plates are made up of both a little bit of mantle and then our last layer, which is the crust, which we'll get to on the next slide. Okay, so crust is the top layer. It is the thinnest. It's only 6 miles deep. Well, to 35 miles deep. It's mostly made of silicon, oxygen, and a form of quartz. There's two different types of crust. We have oceanic crust, which forms oceanic plates. It's going to be a lot more dense, a lot heavier, made of a basalt type rock. And then we have continental crust, which is less dense, and it's made out of granite type stone. We're going to be looking at a lot of pictures of the different types of plates, but here again we can kind of look at some of these layers we just talked about. So the asthenosphere is the part of the mantle that's going to have the magma. It's going to be very liquidy, very plasticky. And then the lithosphere is going to be this stuff that has the uppermost part of your mantle and the lowermost part of your crust, and it's going to be making up your plates. So here you can see some oceanic crust, some oceanic plates that are being moved apart, and again we're going to talk about that here in a second. Here we have some continental plates that look like they're being pushed together. Here we have some volcanoes forming in continental crust. So again, we're going to get into all of those different scenarios that can happen with different types of plates. And this is just one more picture showing you our four different layers. So inner core is solid, outer core is liquid. Your widest layer here is the mantle with a solid bottom part and that flowing top part, and then you have your crust. Okay, so plate tectonics, what are they? It was a theory developed in the 60s about movement that happens with plates. And this guy Wagner, we'll get to him in a second, he said that crust is not one large piece, but it's broken into many large segments called plates. They move due to what we call convection currents that are happening in this asthenosphere, the molten part of the mantle. So we've talked a little bit about convection currents, convection cells. We talked about the atmosphere. It's the same idea of what's happening here in the mantle. What's happening is you have segments of your magma that are getting superheated, and when they're being superheated, they flow upward because we know hot things rise. And then when they reach the surface area, they diverge apart from each other from one side to the other. And as they make their ways this way, away from each other, the magma cools down and they sink again, and then they're reheated by the core. They flow upward again, and it's this continuing cycle. So you've got all these series of convection cells next to each other, convection currents. And this is going to cause these broken up plates in the lithosphere to move around in different ways. So some of them we can see are going to be pushed underneath of other ones. Some will be pushed over top of them. Some are actually going to be ripped apart, where magma is actually going to be able to come up through this surface. So we have lots of different types of movement. Okay, we are going to talk about Pangea and just movement of plates. We're going to do a pretty cool activity in class. So here we can kind of see how our crustal plates have actually moved around throughout time. 225 million years ago, Pangea was believed to have been where it's called a supercontinent, where all of the continents were joined together. And we see them starting to move apart from each other here in the Triassic period. Here we just kind of had two big chunks of land, Laurasia and Gondwana land. I always love that term. Here we see them starting to split apart a little bit more in Jurassic, a little bit more in the Cretaceous, and then here's our present day with all of the separate continents that we now know. However, something you should know is that these plates do continue to move, continents do continue to move further apart from each other. So again, we'll do a really cool activity in class where we'll get to see how they fit together and how they continue to move. Here's another picture just kind of introducing us to this idea that we have magma that pushes these plates in different directions. And again, I don't want to get ahead of ourselves too much, but here we can see where we have two plates diverging away from each other. These are actually two oceanic plates diverging away from each other. Here we're forming a rift where magma can actually come up through this, and we're actually going to form new crust here constantly as these plates are being pulled away from each other. Here we have two plates converging. So we said these are diverging, they're moving away from each other. These ones are converging. It's called a convergent boundary. What we have happening here is you have an oceanic plate submerging below a continental plate. This plate is going to be melted. That's going to form back into magma. And what you end up happening here, a lot of times you end up getting a mountain range from them squishing together, and this molten magma coming up and forming volcanoes in this mountain range. Okay, so this is just another slide of Pangea, the supercontinent of all the continents together. This is a chart of geologic time. We are actually going to do some activities with this later on in this unit, but it just kind of shows you some of the major eras and periods and what sorts of things came about. And one of the things that we'll talk about is how humans are really, we're just the infants of geologic time. We have just arrived, and that's an interesting implication for this class because we've already changed this planet so much, and having just arrived here, it's an interesting thing to think about. So we'll come back to that later. Let's move on for now so these notes don't get too long. Okay, what we're going to talk about now is evidence of continental drift occurring and evidence of plate tectonic theory. And again, this was introduced by a guy named Wegener. Okay, so our first bit of evidence that continental drift occurs, that these plates are constantly moving away from each other, is that if we match up South America and Africa, we find that they actually have chunks of rocks, which they say that they're only found in certain areas under certain conditions. These rocks, where you can see their shapes kind of fit together perfectly, these rock bands also fit together perfectly. Okay, and again, it would be hard to believe that this is just a coincidence that they've got these pieces of rock that only occur in certain parts of the world that match up perfectly with each other when their shapes seem to match up perfectly with each other as well. Okay, so we kind of just talked about this, but many of the continents, their shapes fit together like a puzzle piece. The most obvious being South America and Africa. They look like they fit almost perfectly together. We've also got some other countries that, and again, you guys are going to do this with paper too, when you arrange them in a certain way, they fit together very, very nicely. So here's your South America and Africa again, North America, Greenland, and Europe. They all fit together very nicely. This is probably one of my favorite ones. This is really cool. Similar to the matching rock bands, when we put the continents in the correct order that we believe them to once have been in, they also have matching bands of fossils. And we have several examples of these. Okay, so again, if we match up South America and Africa like we believe that they used to fit together, we've got this banding pattern of these. I don't even want to try to pronounce what they're called, but they were a land reptile. Again, only found in certain parts of the world, and here's their range that we found their fossils in. It matches up very nicely. The Mesosaurus, okay, same thing. South America and Africa, right where we thought they would meet together. This is where we find their fossils. We have Lystrosaurus. We have banding pattern in Antarctica, India, and Africa. And then this fern is interesting for a couple of reasons. Not only do we see the banding pattern throughout a couple of continents here, Australia, Antarctica, India, Africa, and South America, but also ferns are a tropical plant, and we're finding these remains in continents that are definitely not tropical anymore. So that's showing us that a continent like Antarctica probably used to be closer to the equator in order to have a tropical fern as a fossil within it. Okay, this again kind of ties into what we just talked about with the fern, ancient climates. We do find continents now that were never in a warm tropical environment or never in a cold environment. They're going to show evidence of remains of things from those types of environments. So ice sheets on continents, tropical plant fossils found in Antarctica. Okay, places that show that continents used to be somewhere on the planet, but now they've moved to a different location. Okay, this one's pretty cool too. This is evidence of seafloor spreading. I know we haven't talked about these divergent plates and the magma coming up from them much yet, but we'll get to that in a second. We'll learn that when you have two plates rifting apart from each other, moving apart from each other, magma comes up. And something that's kind of interesting is that our poles, the North Pole and the South Pole, they actually kind of flip-flop over the years as to which way the magnetic field is going to pull. So what we end up getting is on both sides of this rifting, this diverging, this magma that comes up. If we look at like this blue piece right here, when the blue pieces came out, the pole was going in one direction, so the magnetic field is headed in one direction. And then later, the pole started coming from the other direction. So these yellow bands were being pulled in the opposite direction. Then this newest one then is going to go back in the opposite direction. So we see these alternating bands based on which pole is having that the greater magnetic pull to it. Okay, so here you can see normal polarity, reverse polarity. And again, these come in twos, so it says equal distances from the rift valley are going to have the same polarity and the same age. So we can tell where this rifting is occurring, and we can see these equal dated bands in the same direction of the magnetic pull in those bands. Okay, and this picture shows the same thing. Again, these things are being reversed or they're being normal, and here's where the actual magma is coming up. Okay, and then this is kind of similar. We had a drilling ship that went down, and it says it's found that the youngest rock is always right near that rift zone, right near where the plates are diverging. And then they get older the further you go away from them. So we can see here these dark lines are representing where the plates are diverging away from each other. All the red pieces, that's all new crust, young new crust. The yellow ones are going to be kind of medium in age, and the blue is going to be very old, so they're the furthest away. Okay, so we always get the newest, youngest rock right from where the plates are diverging. Okay, this is a really great picture, a really important slide. So here's our breakdown of the 3 different types of plates that we have and the different interactions that we have. We have a divergent plate, and just like it sounds, if something's diverging, it's being pulled away. We have convergent plates, and that's where 2 plates are colliding. Then we have transform plates, where 2 plates are actually just sliding next to each other. So these are the transform plates. This is what's going to give us earthquakes. So we'll talk about that in a moment too. Here's divergent, they're being pulled away. Here's convergent, they're being pushed together. Again, we've looked at this picture kind of before, but here's a picture of divergent, where 2 plates are being pulled away from each other. Here's a picture of convergent, where an oceanic plate is falling underneath the continental plate. And then the same thing's happening over here. Actually, this is oceanic underneath of continental. This is 2 oceanic plates. And all of these different interactions cause different things to occur. So let's go ahead and get into those. Okay, so as we just said, divergent is where plates are going to move apart from each other in opposite directions. When this happens, the magma actually comes up through that new opening to fill the void where the plates are separated, and new crust is being made in these instances. So the types of landforms that would form when 2 plates are diverging from each other, we get underwater mountain chains called mid-ocean ridges. I'll show you a picture of that. On land, we get what's called a rift valley, where actually the land is moving apart from each other. And again, we have some good examples of that. Some specific examples are the Mid-Atlantic Ridge, the African Rift Valley. Iceland's got a really cool rift valley, and then Baja California also does too. And these are all near divergent plate boundaries. Okay, let's see. Here we have the Mid-Atlantic Ridge. It's this huge plate boundary that goes down the middle of the Atlantic, just like it sounds. These plates are being pulled apart from each other, and you've got this huge underwater mountain chain forming from that ridge. Okay, so this is like underwater. Big, huge mountain chain. This is what we call a rift valley. Again, very cool. You've got 2 continental plates being pulled apart from each other. New magma is able to come up here and harden and form land, but you can see it's this big, huge valley, much deeper drop off from where the plates used to be. So we have these big ridges here. Iceland's got a great one. Iceland, this is how it actually formed. It's right over the Mid-Atlantic Ridge. So this is an island that was formed by magma coming up through this, cooling and hardening above the ocean. And we've got this big, huge island. And we've got a lot of volcanic activity. We've got a lot of geothermal heat generated on this country. It's a really neat country. It's like straight out of earth science textbook. This country continues to grow because of this rifting, and also due to other reasons that we'll come back and talk about later on. But we can see these plates are continuing to be pulled apart from each other, so it continues to rift. Here's some actual pictures. Here's another picture that kind of demonstrates how a rift valley would form. The plates are diverging apart from each other. This magma comes up, it hardens, it forms new crust. But we can see every time it kind of rifts back, we get lower and lower and lower. It's subsidence. This is an aerial picture of Iceland's Rift Valley. It's actually on land. I'll show you some real-life pictures of it. There are buildings and structures around it. But people know not to live nearby it because it's kind of active land. It happens very slowly, but this is over the ridge where this land, I guess I can draw, we can see it's probably right in here where this is happening. These are some borders of these rifts, kind of like what we're seeing up here, these little edges. So these are some rifts here, and you can see that stuff used to be in the middle, and it is slowly creeping outward. Here, this looks like this is another ridge, and this is another ridge. So we're actually expanding this land. It's this big, kind of deeper, subsided, flat valley that's forming because we're rifting that land apart. Okay, here's just another picture of Iceland, and again, you've got this rift zone. I believe where that picture was being taken, it's down here, which is kind of interesting because Reykjavik, the capital, is right around over here. So a lot of this activity is actually happening near the capital. This is a picture of some of that rifting, some of those ridges of the rifts that we looked at in that cartoon picture on the last slide. This is called the Great Rift Valley in Africa. It's the same idea. You've got this big, wide, kind of subsided area, and you can see that this is still actively moving. Here's a map of it right here. It's over here near the Red Sea, but you can see where the land is actually still moving apart, rifting apart, because you've got a divergent plate right there. Okay, a convergent plate boundary is where two plates are going to collide. Here we form what's called a subduction zone, where one plate goes up under the other plate. And it says a lot of times the plate that rides on top is the continental plate, and the plate that subsides is usually oceanic, if it's those two types of plates. But you can have an oceanic subsidence, and you can have a continental. So we'll look at both of those too. What happens when the oceanic plate goes under is that it moves into the asthenosphere, it becomes melted, it forms more magma. This can form a couple different things. This can cause a deep sea trench, we'll see pictures of that, and it can also form really steep-sided volcanoes that we call composite cone volcanoes. It says these two things occur when continental and oceanic crusts collide, or where oceanic would collide with continental, which is the same thing. So, if continental collides with continental, we form folded mountains. And again, we'll look at those. Some really good examples of those are the Andes, also the Himalayas, I think is what I have pictures of. Example of a really famous trench is Marianas Trench. And some examples of some of these steep-sided composite cone volcanoes that we just mentioned are Mount Everest, Mount St. Helens, Mount Fuji, Mount Vesuvius, and the Ring of Fire is just a really good example of convergence anyways. Okay, this picture right here is showing us what would happen if you have an oceanic plate convergence. So both of these plates are ocean. One oceanic plate subsides below the other one. We form a trench, which is this little dip here. This plate's going to be melted. We said it'll be melted into magma. That'll heat underneath of this plate. That's going to cause this magma to rise up, form volcanoes. Okay, and then these would lead to what we call volcanic island arcs, and we have some good examples of that in another few slides. Here is an example of oceanic continental convergence. Kind of similar, but instead of forming volcanic islands out in the middle of the ocean, here you're going to form volcanic mountain range on the edge of the continent. So again, oceanic crust goes below, we form a trench right here, this plate is melted, forms magma, it pops up here, it forms this volcanic mountain range. Okay, but it's on land. This volcanic range is out in the middle of the ocean. And then here's when you have two continental crusts converge. You just have folding of the land. So imagine two things are crinkling together, almost like a car accident. Okay, you got two cars crinkling together. You're going to have this uprising, and you form a mountain range. And again, a good example of that are the Himalayas and the Andes. Okay, the volcanic island arcs. Very cool. These happen, we said, mostly at oceanic convergent boundaries. And again, so you've got one plate subsiding under the other one, and that's going to cause magma to melt, and it's going to form volcanoes. Yeah, you can have those, that's fine. Some really good examples of volcanic island arcs are Japan, which I do not have a picture of, but you know what Japan looks like. The Philippines, which are actually pretty near to Japan, and I think I have a picture of them later in the presentation. And then we have the Lesser Antilles Islands of the Caribbean. And a lot of times they actually form this arc shape too. So this is, if you've ever been to the Caribbean, these are some of the islands that you might have seen. Okay, hotspot volcanoes. These are going to be different from volcanic arc islands because a lot of times these can actually happen in the middle of a tectonic plate. It doesn't have to be at a boundary. It could actually be in the middle of a tectonic plate. what happens with these is that you have a plate where there's just a really, really hot upwelling of magma in the middle of the plate. And that hot magma actually kind of comes up and burns a hole through the plate, and that will create volcanic islands out in the middle of a plate. An excellent example of that is Hawaii, because Hawaii is not on a plate boundary. Hawaii is in the middle of a plate, and I'll point that out to you on one of our next slides. It just happened because, again, basically a big ball of magma formed under the plate, and it was so hot that it caused these islands to form. And again, all these plates are moving, so that's why you see them actually kind of trickling off here, because the plate is moving. So these ones would be the oldest islands, and then these ones down here right over the hotspot would be the newest ones. We have Galapagos are formed by hotspots, and then also, even though Iceland is on the Mid-Atlantic Ridge, they say I think it's the lower southwest edge is actually a hotspot forming it too. So Iceland's got a lot of cool stuff. All right, this is a great picture. This is a picture of all active volcanoes on the planet, and it also shows all of our plate boundaries. So something you should really pick up right away when you look at this, look where we see most of your volcanic activity. Okay, all these little red dots represent volcanoes. Look, most of them are right over the plate boundaries, and we should understand why that is, because a lot of times volcanoes are formed when a plate subsides underneath of another one. You melt the crust and it comes up and it forms a volcano. These are all volcanoes, either active or inactive, but they're all right on these plate boundaries. Now, looking out here, there's Hawaii. Again, not near any sort of plate boundaries. They formed due to hotspot. So just hot magma that came up and it burned a hole through that plate there. Okay, we can see other hotspots around the world too. Over here here's Japan, okay, and your Philippines would be around the same area. So a lot of those are right on these plate boundaries as well. Here's the Mid-Atlantic Ridge we talked about. So just a really, really great picture. And Ring of Fire, something else I wanted to touch on here. We have a lot of activity. Most of this volcanic activity is going to be happening here in this Ring of Fire, which is out in the Pacific. Okay, here's continental versus continental. Best example I think is Himalayas. They are the highest mountain range in the world right now. Something cool about them, these plates continue to converge. They continue to get higher and higher. Continental versus oceanic. So again, another good example of this is the Ring of Fire. We have a lot of trenches here, a lot of trenches. Here we have the Mariana Trench. We said it's out here in the Pacific near the Philippines. Okay, it's a big, huge trench where that convergent plate is. Which, can you see it in this picture? Yep, here it is right here. Okay, and a whole bunch of other trenches where we have a lot of convergence. Mount St. Helens, out in the west of our country, is a good example of convergence. And then we said this is Mount Vesuvius in Pompeii. This is Mount Rainier out in Washington. Okay, so again, all of these mountains, they all have volcanic activity too. Oceanic versus oceanic, a good example of this is Mount Pinatubo in the Philippines. And this shows a picture of its eruption back in the 80s. It was a pretty powerful one. And the last boundary is called a transform boundary. This is, instead of plates diverging or converging together, this is where they actually slide past one another in parallel directions. What you experience here is you experience earthquakes. Basically, imagine two things kind of being locked together, stuck together, and they're just twitching. They really, really, really want to separate. It's almost like a piece of elastic. And then it finally breaks loose. It's going to send a rumble through the crust, and that's what generates this earthquake. Okay, so a really good example in our country is the San Andreas Fault out west in California. So again, you see these two plates kind of rubbing up next to each other. They're stuck, and finally they break loose. That's going to send this, this aftershock. This, I don't even want to call it an aftershock, because you have an aftershock with earthquakes, but it's going to send this. I don't have a good word for it right now, but it's going to cause an earthquake. There we go. All right, so here you have the San Andreas Fault down the west coast of California. And again, here's one plate sliding this way, here's one plate sliding this way, so you could see how that would generate an earthquake. Rebound effect, that's what I was thinking. Once the plates slide past each other, they have this rebound effect. There we go, that'll work. Okay, and the last slide here again, one more picture of the San Andreas Fault, and then there's an actual picture. Okay, I think that's going to be it for today. We'll pick back up with that slide, resources and minerals, on another day.